Hi there. In this video we're going to learn a little bit about trees and connected graphs. So to get things started, a tree is a connected graph that has no cycles in it. If you'll remember, a cycle is when there is a path of edges that leads back to some starting point. This is an example of a tree. It doesn't have any cycles. That is, you can't go from here to here and then there's no, like, say, point here that would lead back up to here. A graph that does have cycles would be an example of, or would be like this one. This is an example of a graph with cycles. This triangle here constitutes a cycle. So just to keep in mind, a tree is a connected graph that has no cycles. Oh, connected meaning that from any two vertices on the graph, you can get from one to the other with a path. So to get from this one to this one, we can go from here up to here, down to here. And so that's a tree. Alright, so for what follows, for everything that follows, we'll let G be the graph with the vertex set V and the edge set E. Okay, so here's a first initial property of connectedness in graphs. If G is connected, then the number of edges is greater than or equal to 1 less the number of vertices. And the demonstration of this involves constructing sort of inductively graphs. So if we have just one vertex in our graph, it's just represented by this single point, then the number of vertices is 1 and the number of edges is 0, and so the number of edges 0 is greater than or equal to 1 less the number of edges. So 0 is greater than or equal to 0. Now if we add another point to the graph and connect the 2 points together, then we have now a connected graph with two vertices, and so the number of edges is 1, and that is greater than or equal to 1, which is the number of vertices minus 1. 2 vertices minus 1 is 1, and 1 is greater than or equal to 1, so the property holds again. Now if we add another point, this time we can choose either of 2 places to connect to the graph. In this example, I just sort of showed a dotted line here where you could connect if you wanted to, and I chose to only connect in one place. So now we have 2 edges, 1, 2, and 3 points, 1, 2, 3, and so again, 2 is greater than or equal to 1 less the number of vertices, which is 2. So we add now a 4th point. You can kind of see where this is going. You add a 4th point, and this time I decided to connect to 2 places instead of just the 1, just to show that sometimes this value is actually bigger than 1 less the number of edges. So we are 1 less the number of vertices. So we have 4 edges here, 1, 2, 3, 4, and that is greater than or equal to 1 less the total number of vertices, 1, 2, 3, 4. So 1 less the total number of vertices is 3, and the property holds again. So the basic idea is that if you keep this graph connected as you keep adding more points, then every time you add a new point, you have to connect to at least one of the other points, which adds at least one more number of edges, which keeps this inequality true. So we just sort of did it here for 4 examples, but you could see that we could just keep doing this on into infinity if we wanted to. Okay, so next property here is that if the number of edges is exactly equal to 1 less the number of vertices, then G is actually a tree. That is, G has no loops in it. So we can actually see this up here. If just in this last step I would have continued to only connect at 1 point, then we would have continued to have exactly 1 less the number of edges. 0 and 0 were here, and 1 and 1 were here, and 2 and 2 were here, so there was an actual equivalence here, not just an inequivalence. And here we ended up with 4 greater than or equal to 3 instead of 3 greater than or equal to 3, because I added 2 lines, or 2 edges when I connected this point, but I could have just added 1, like I might just, for the sake of demonstration, delete this one and pretend that I didn't add it. It's still connected. We have this all connected up, and now we have a tree because we don't have any loops. Okay, so now we get to the reason why we care about this, the concept of a spanning subtree. So if this is a graph here, we see that this graph is connected. We can actually delete edges so that we end up with a tree and it's still connected. So here's the graph A, B, C, D, and it has these 4 edges. If I delete either this edge or this edge, I end up with a tree, in this case this tree here, or in this case this tree, such that it's still all connected and it still involves all the same vertices, but now there aren't any cycles, there aren't any loops between the edges. And so that is formalized in a property that says that every connected graph contains a spanning subtree. And how do we know this? Well, it's just basically like we did up here. We can start with any graph, this is an example graph, and just start deleting edges. So I delete this one, and delete this one, and then delete this one, and then delete all of them until we end up with a tree. So you just keep deleting edges such that every time you delete the edge, you don't ruin the connectivity property, and as you're deleting, you stop as soon as you have exactly one less the number of vertices. As soon as you have one less the number of vertices edges. So as soon as this equivalence is true, then you stop deleting edges, and then you know you have a tree. So that shows that every connected graph contains a spanning subtree. It's said to span the subtree because it includes all of the same vertices, and so that's trees and connectedness. All right, thanks.